Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 32, and it is entitled The Work-Energy Principle. We finally get to our statement of the work-energy principle in the most generalized way that we're going to see it. Before we state it, let's remind ourselves of some things that we know. First of all, the definition of work. Now you'll remember that this formula, work is equal to force times displacement, is valid when the force is constant over the distance that's being moved. So I can't calculate the work done, say, by a spring when I stretch or compress it using this formula because that force is not constant. We need to remind ourselves about conservative and non-conservative forces. We have encountered only three conservative forces so far. They are the weight force, the spring force from Hooke's law, and the electrostatic force. All other forces that we've dealt with are non-conservative forces. So contact forces, the normal force, any kind of pulling force, tension, anything else besides these conservative forces are non-conservative forces. Now we're ready to state the work-energy principle in its most generalized form. And here's what it says in words. The non-conservative work that's done on a system is equal to the total energy change of the system. This is a powerful, powerful equation, and there's a lot that's wrapped up in it. Basically, the NC subscript on the work means that I'm just dealing with non-conservative forces. So basically, not the weight, not the gravitational force, not the electric force, not the spring force. But if I compute all the work that's done by all the other forces and then look at the change in the total energy, and we've talked about kinetic energy, gravitational potential energy, elastic potential energy, then I can equate those two things together. That looks like a very simple formula. We're going to see it work itself out in the next four examples, and that's what we want to do next. Let's apply the generalized work-energy principle to four specific examples. Here's the first one. Example 32.1. A man pushes a 20-kilogram box of tools 5 meters across a level floor with a force of 100 newtons. The force of kinetic friction between the box and the floor is 40 newtons. If the box starts from rest, find the speed of the box after it has moved 5 meters. Let's sketch a diagram of this situation and then look at the forces that are acting on the box. The box starts from rest, and it starts at some position on the floor that I'm going to call x equals 0. The man pushes the box across the floor, and it ends up 5 meters to the right of where it started. So we can say the displacement of the box is 5.0 meters. Now let's look at the forces that are acting on the box. Let's sketch a free body diagram. This black dot over here represents the center of gravity of the box. I have four forces that are acting on this box. One of them is the pushing force, and that pushing force, they tell us, is 100 newtons. That is a contact force. It is non-conservative. There's the frictional force. It is opposing the motion. So if the box is moving to the right, the frictional force is to the left. And we're told that that frictional force is 40 newtons. That's a non-conservative force. We have the weight. The earth pulls the box downward. Since it's a 20-kilogram box, the weight is going to be m times g. It's going to be 200 newtons. That is a conservative force. And there's the normal force. The floor pushes upward on the box, and if my pushing force is horizontal, then the normal force is going to be equal to the weight. It's also 200 newtons. That is a non-conservative force. Now what I'm going to suggest to you is that the displacement is completely horizontal. So there are only two of these forces that are going to contribute to the work. One of them is the pushing force, the other is the frictional force. Certainly the weight force and the normal force are acting, but they are perpendicular to the direction of motion. Since the pushing force and the frictional force are non-conservative, then I can write the non-conservative work that's due to those forces and apply the work-energy theorem. Here we go. There's the work-energy principle. The non-conservative work is equal to the change in the total energy. Well, what kind of energies can we have here? We're not changing elevation, so there's no gravitational potential energy. There are no springs or rubber bands involved, so there's no elastic potential energy. The only kind of energy that's involved here is the kinetic energy. Now I notice that the pushing force and the displacement are in the same direction. So I'm going to get a positive contribution to the non-conservative work due to the pushing force. The frictional force is in the opposite direction to the displacement, so there's going to be a negative contribution to the work due to the frictional force. And I'm going to set that equal to the change in the kinetic energy. Here's how it looks. Now you could write that work due to the frictional force as plus a negative frictional force times the displacement because of the direction of the frictional force. I'm writing it with a negative sign there because I see that the direction of the frictional force is opposite to the displacement. So now kinetic energy is 1/2 mv squared. Let's feed that in. I'm told that the box starts from rest, so I can write that the initial velocity is equal to 0. And now what am I trying to find? I'm trying to find the final velocity, the final speed, if you will, to the right. So I can solve this equation for the final speed. If you'll permit me, I'll do it all in one step. And now I'll put in the numbers. And I get that the final speed is equal to 5.48 meters per second. Does this object accelerate? It sure does. We see that because the initial velocity is 0, the final is 5.48. We have some net force of 60 newtons on it. We could actually do an F equals ma and an equation of motion to figure this out, but here we have done the work energy principle. The next application, example 31.2, should be 32.2. A 2 kilogram object starting from rest slides down a frictionless 30-degree incline whose vertical height is 1 meter as shown. How fast is the object moving when it reaches the bottom of the incline? Now let's notice something about this situation. There are only two forces that are involved in this because we have a frictionless situation. There's the weight force that acts straight down, and there's the normal force which acts perpendicular to the incline. The weight force is a conservative force. The normal force is a non-conservative force, but it is perpendicular to the displacement delta D that's along the incline. And so it's not going to contribute anything to the work that's done on the object. So basically, when I write the work energy theorem, which I'm about to do here, there are no non-conservative forces that are going to fit into this equation. In other words, the left-hand side of this equation is going to be equal to 0. What about the right-hand side? What kinds of energy are involved? There's gravitational potential energy, the object's elevated by 1 meter, and there is kinetic energy. On the left-hand side, there's no non-conservative work. On the right-hand side, the change in the total energy is the final energy, which could be kinetic and gravitational potential, minus the initial, which could be kinetic and gravitational potential. Some of those are going to be 0. So I could rewrite this in terms of the formulas for kinetic and gravitational potential energy. I notice that the masses are going to cancel out here. So I'm going to solve that formula for the final velocity at the bottom of the ramp, the final speed. And now I'll substitute the numbers. And I get that the speed at the bottom of the ramp is 4.5, just under 4.5 meters per second. Let's go to example 32.3. Here's the problem. The incline above is used again, but this time the force of kinetic friction is 1.73 newtons. Find the speed of the object when it reaches the bottom. Let's sketch a free body diagram of the situation this time. Now in this case, I still have the weight that's acting. It's a conservative force. I still have the normal force. It's non-conservative, but again, it's perpendicular to the displacement. On the other hand, the frictional force is non-conservative, and it is anti-parallel to the displacement. So it's going to contribute something to the non-conservative work. It's actually going to contribute a negative value to it because it's in the opposite direction to the displacement. So let me write the generalized work energy principle. The non-conservative work is equal to the change in the total energy. And now let me substitute in what those things are. The non-conservative work is due to the frictional force, and since friction acts in the opposite direction to the displacement, I'm going to put a negative sign in for that non-conservative work. At the top of the ramp, I've got a combination of kinetic and potential energy. The kinetic energy is 0 at the top. At the bottom of the ramp, I have a combination of kinetic and potential energy. The potential energy is 0 at the bottom. I can write this in terms of the formulas for kinetic energy and gravitational potential energy. Let me write the next line. And now, if I could figure out a number for D, then I would know all the numbers in this equation, and I could figure out what the final speed is. Well, I can figure out what that D is from the geometry of this right triangle. I can say that the sine of 30 degrees is equal to 1 meter divided by D, and so I can figure out what that distance is. The sine of 30 degrees is the opposite side of the angle, 1 meter, divided by the hypotenuse, which is the distance D that I'm looking for. Your authors call it delta D. I've put it as D in my formula. So D is going to be equal to 1 meter divided by the sine of 30. So the object slides 2 meters along the ramp. I'm going to use that information now to figure out what the final speed is. Going back to my work energy principle, I can solve that equation for VF. I'm going to do that in one fell swoop, and then we're going to put in the numbers. All right, so I've done a whole mess of algebra here at once. I added mgy to both sides, then I multiplied both sides by 2, divided both sides by m, and then took the square root to figure out what the final speed's going to be. Now, let's put in the numbers. I get that the final speed at the bottom of the ramp is just under 4.1 meters per second. This makes sense. Friction slows the thing down. It's not moving as fast at the bottom when friction acts as it was at the bottom when there was no friction. You remember in the problem before, we got 4.5 meters per second. Now we're just down to 4.1 meters per second.